probably we will take next 30 minutes and hopefully shorter than that to go over rest of the epi lecture, and we will talk about difference between RCT, randomized controlled trial, versus observational studies. Yeah. So this is an example from a prospective cohort study. So now I can use a technical terminology. It's great. So data are from a Cleveland clinic, and patients are followed from 1990 to 1998. And for the patient and who had echocardiography for known or suspected coronary disease. Okay? And then they are followed for median of 3.1 years for the outcome of death. Right? So maximum follow-up time is 80 years. Okay? So this is the data from observational study. And this is a typical observational study. So the result of this study, what they did is they conducted the survival analysis to time to death, and hazard ratio is 1.08. What is a hazard? And a hazard is instantaneous risk of events. So it's sort of average risk of death over follow-up time, which is 1.08. So this means if you, they're comparing aspirin, because again, the PECO. What is a P? In the patients who has echo for known or suspected coronary heart disease. And E, what is E? Aspirin use. What is C? And non-aspirin use. What is O? That's a death. Okay. And this is a prospective cohort study. So they had a time to death as an outcome and conducted Cox regression and gave a ratio for instantaneous risk of dying. So aspirin, if you have aspirin, and it increased risk of dying by 8% compared to people who do not use aspirin. Okay? Do you believe that? P-value was 0.5, so you probably say, well, 1.08, but I can't say anything, so maybe the same. So can you say aspirin didn't work? Didn't harm, but then didn't work either, right? So is that true? Do you stop prescribing aspirin? Well, this is observational studies. I have to see who are compared to who. So this is the baseline patient characteristic table, and then font are a little bit small, so I hope you can see it. So they, at the baseline, they divide the patients to 2,300 patients with using aspirin, and the rest of it not using aspirin. Okay, the mean age for aspirin users is 62 years old, and mean age for non-aspirin is 56. Okay, outcome is death. Right, age is different. And 77% of aspirin users are men, whereas 56% of non-aspirin users are men, right? And let's see, hypertension, 53% versus 41%. And let's see, coronary, prior coronary artery bypass graft, 30 to 6. Oh, that's a lot different. And then how about coronary disease? This one. Prior coronary artery disease, 70% of them have it if they use aspirin, and then only 20% if they don't use aspirin. 70% versus 20%, the history of heart disease. That's a huge difference. Okay? So these are, you can see other things, and almost everything is different, right? So what does this mean? People who use aspirin, they had the reason to use aspirin. So their doctors are good, right? They are prescribing aspirin because there is a reason, right? So now you know these two populations are different, a lot different. And then I show you this. What do you think? Do you still think aspirin did not work? Long-term survival is similar. Nevertheless, these two groups are a lot different, which means aspirin worked, right? With that aspirin, that hazard ratio, okay, could be as worse as, okay? Do we have clinicians who make a guess? Given this much difference, okay, right? Forget about aspirin and no aspirin. You know these two patients are different. These group are much sicker than this group. And what do you think? Even without aspirin, how much risk, how much more risk in people with this group have compared to that group? 1 can be 1. Probably 2, right? So with that aspirin, hazard ratio could be as worse as 2, but with aspirin, it is 1. What does it mean? Aspirin probably worked. Yeah. So if you didn't look at this, you were almost making wrong conclusions. Say aspirin didn't work, right? So this is called unadjusted analysis. So you ignore the difference between two groups, but all you did is to compare outcome between two groups, aspirin and non-aspirin. Okay? And then this is a biased result. Okay? How is biased? Because aspirin users are sicker, so we are comparing orange apples to oranges, right? We didn't compare apples to apples. So if you ignore that fact, we make wrong judgment. This is called bias. This is called confounding. Okay? So confounding is a bias which can be caused by difference between two groups. And if analysis ignore those difference, okay, and then we might be seeing misleading result. Okay. So in this case, okay, factors which are unbalanced between aspirin and non-aspirin, let's say age, let's say sex, and let's say the history of heart disease or hypertension, diabetes. These factors unbalanced between these two groups, and these are called confounders. Okay? So age may be confounding result of effect of aspirin on the death, and because age is different between two groups. Okay? So this is the limitation of observational study, because there is no randomization. So we might be comparing apples to oranges. Okay, so that might put you in the wrong result. Okay, so the challenge in observational study is analysis. We do have to adjust for these differences. Okay, and right. So typically, what we do is a randomization. Yeah.
So if you would have reviewed his paper, and you rejected it.
Yeah, of course. Yes, of course. Yes. So who believed this? Yeah, you wouldn't believe this, right? And in abstract, you have to say what is the study design. So study design, observational, prospective, cohort study. Okay. So that means there's no guarantee you're comparing apples to apples. And then the next part, I look at statistical section. Statistical section, there is no adjustment for confounders, there is no mentioning for confounders, and that's clearly out. Okay. I don't completely reject because statistical analysis, you can still redo it. Right? If you have wrong design, that's probably reject forever because you can't go back to collect data again. But if you have a right data but wrong analysis, and you can reanalyze and resubmit. Okay, so that's a very, very typical advice since we make. So adjust for confounding. So what they did is, of course, they didn't. It was published in JAMA, so they didn't do. They didn't finish analysis right there, and so what they do is statistical adjustment. So the reason we do regression is really the adjusting for confounders. Okay, so if you don't worry about confounding, and you have a beautifully balanced table 1, aspirin and non-aspirin users are nearly identical, then you might not worry about regression. And You might just do Kaplan-Meier curve and compare two groups and finish your analysis like that. But this is an observational study, so they didn't do that. So what they did is that they use a Cox regression and adjust for age and sex. So remember, mean age is 62 for aspirin and 56 for non-aspirin. So what do you think can happen if you adjust for difference in age? Okay, or in sex? Okay, more male among aspirin and less male for non-aspirin. And hazard ratio actually moved toward showing effect of aspirin. So 0.75 means 25% risk of instantaneous chance of dying. I mean, I would just say risk. 25% risk of dying is decreased by aspirin, and which is statistically significant. So now we have good evidence, right? But then if say baseline balance, no, it's not just age and sex, which was unbalanced. I'm not convinced. So why don't you adjust for history of CAD? Okay, so if you adjust for history of CAD, the ratio become 0.57, and that means 43% of risk of dying. Okay, risk of death is reduced by having aspirin. And p-value is less than 0.001, right? And how about other? There are many other factors which are not balanced. So what they did is they put everything in the model. And making adjustment is very easy. If you have a software like SPSS, you have a huge box for independent variable. And you just stack in these variable. Just point and click and move it to a box, right? So they put all of this in the Cox regression. In the final Cox regression, the result is 0.67. Okay, is that intuitive? Actually, I wonder why hazard ratio become bigger in this point. It's still statistically significant because p-value is 0.002. But after you start putting like beta blocker use, lipid lowering drug, and many drugs, and then this become less of effective than this just this analysis. Is that intuitive? Actually, it took me a while to think. I thought hazard ratio keep decreasing by putting more variable in it, but actually therapy, people who are using aspirin, they are on other therapies too. So the reduction of deaths might not be just due to aspirin. It could be helped by using other drugs. Okay, and so those are included in the regression. So therefore, for some variable, lower hazard ratio, some variable, enlarged hazard ratio. So at the result, they end up having 0.67. And we call this adjusted hazard ratio. So adjusted for confounding. So therefore, you don't have to really worry about difference between two groups. Okay, so we use a statistical technique, mathematical technique, and to adjust the difference between two groups. All right. So what actually happened is, okay, so mathematics, statistics, and what they did is that they know age is 6-year difference, and then percent of male is this much different, and percent of diabetes this much difference. So they can actually compute effect of each of confounders to the death independently. Okay. So if age is increased by 1 year, and that translates to increase in risk of, let's say, 0.5%. Okay, so therefore, aspirin group have a 6 years older age, so that contribute to 3%, for example, increase in the rate of death. And then analysis actually discount that, right? So any excess increase or decrease risk of death by aspirin, given these unbalance, mathematically they compute it and then remove those differences. And then the leftover, it was used to compare effect of aspirin. Okay. So it's easy to do mathematically. All right, so adjustment, that intuitive now? All right. So then, right, observational study is very important to adjust for confounding, and hope I convinced you enough. And so let's see what happens if you can randomize patients. So this is a similar study, and they looked effect of aspirin. Okay, so for now, forget about vitamin E components, but for outcome of death. And then this study, and they grab the patients, and then for each patient, they flip the coin, or they use a computer random number generation. And then 50% chance a person get aspirin or not getting aspirin. And this is the baseline table. It's kind of small. Okay, I tried to enlarge it, but I hope you can see it. And randomization preserve balance between two groups. Okay, so therefore, you're comparing apples to apples. So you might not use regression to make adjustment. So you might just draw a Kaplan-Meier curve, okay, to compare profile of death over time between aspirin and non-aspirin, and then compute the p-value. Okay. So regression is less important for RCT than observational study. But although you could make analysis more efficient if you use regression, even for RCT. So I do recommend people to use regressions for RCT. But anyway, I try not to get into too much of detail. But by rough guideline, reviewer don't worry too much about adjustment when you already did randomization. Okay? All right. Okay. This RCT is wonderful, but you have less chance to find a difference. So many RCT end up being a negative. Okay. And there is a reason for that. So this study, relative risk for death between aspirin and non-aspirin is 0.81. So this is a 95% confidence interval, which I will explain when we talk about stats. But anyway, a quick judgment. If 1 is included in this interval, this translates to p-value greater than 0.05. So they are not showing p-value, but 1 is included in this interval. So p-value would be greater than 0.05, and then this is a negative study. So they didn't see the aspirin actually improve risk of death, decrease risk of death. They didn't see that. So why that? Why is that? So we will talk about that. Before we talk about disadvantage of RCT, let's talk about advantage of RCT. Okay? So up to this point, you might see, okay, if you can make, you might see in this way, if you can do regression adjustment for confounding, and what is the value of doing RCT? Okay, instead of hiring a huge group of people to do randomization, you can just hire 10% of Tatsuki's time, okay, to do adjustment. That's cheaper than doing RCT. So can we get rid of RCT? Okay. Just do statistical adjustment for confounding. And then things is not that easy, because the beauty of RCT is, there is a beauty of RCT. Here, using statistical adjustment, statistics, we need the data. Okay, so we can control for imbalance of measured confounding. Okay. So if you are measuring all confounders, you may be okay just to do regressions, but in many cases, you don't collect every single information, right? So RCT is good because it preserves not only measured confounders, it also preserves a problem it could be having from unmeasured confounding. Okay. So by randomized patients, you don't have to actually measure everything, because the randomization principle, we know even for unmeasured factors, randomization preserves balance between two groups. Okay. So that's the beauty of randomizations. Okay. Statistical adjustment works only on measured confounding, but not unmeasured confounding. Okay, so by that, people tend to believe randomized clinical trial is a gold standard for among many study design. Okay, and the guideline committee, they assign higher evidence level to RCT compared to observational research. But there is a problem with RCT. RCT is not always providing the correct information because of this. Okay, so let's start with feasibility. Sometimes randomization is not feasible. Can we randomize people to smokers to smoke and not smoke? We can. Can we randomize people to have delirium in ICU? No. Right? So many cases you can't really randomize because it's not feasible. Yeah? And then more costly. Randomization is a prospective follow-up study. Okay. So it doesn't work for rare disease because you have to wait for a long time to collect enough samples for cases. Okay. And generalizability, so the second. Okay. And have you ever seen many inclusion and exclusion criteria for RCT? This is the inclusion and exclusion criteria for the aspirin study, the randomized clinical trial aspirin study, which is so huge. So more exclusion, inclusion criteria you start using, the result you get from RCT might not be generalizable to general population. Okay. It's applicable to only a limited populations, very similar to the people you would enroll in RCT after using this huge list for criteria. Okay, and so generalizability is an issue with RCT. Okay, the next one, selection bias, or I wouldn't say bias, it's effect. We may have healthy workers effect, and since this RCT require volunteer participations, so people who raise their hands to participate, and they may be the ones who are more health conscious. Okay. And they are the one maybe doing better, okay, in make improvements in their health, right? Or people who are very sick and therefore they are needing to get the therapy. Okay. So the people who raise a hand to participate RCT might be much different from a general population who would have prescribed for the drug in general. Okay, and then the third, okay, Hawthorne effect. What is a Hawthorne effect? Easy terminology for Hawthorne effect. It's a monitoring effect. So the people who participate to RCT, and then they know they are being monitored, and therefore, and then they might improve their behavior just for the fact they are monitored. So while I was at the Vanderbilt for 14 years, and I did have several bitter, hard experiences based on the monitoring effect. So. Anyway, so one time, and I was a statistician for this R18 project, and we followed patients for 5 years, and patients who had diabetes. Okay, so we did educational interventions, and then we're hoping to improve outcomes of diabetes. Okay, so. But anyway, the observational study, and we saw a huge effect. So we thought, no, we can confirm this evidence with RCT. So we began, and then we followed them for 5 years. And after 5 years, we didn't see the improvement. Why is that? So we start digging at data, and then we saw, well, women, yes, we do have a good difference between interventions versus non-intervention. Men, we start losing effect. So men have a smaller difference. Yeah. Especially it looks like men with the control, okay, are doing better than we expected. Men with intervention did okay, yeah, as we anticipate. But men with the control, without intervention, did also better. Why is that? So we have a big meeting. And then a PI said, well, the nurse was pretty. She's very pretty, actually. Okay, let's explain. Yeah. All right, that's it then. So I'm sorry, statistics couldn't help. So that's one thing I learned. Less invisible, so don't hire a pretty nurse. Or monitor less often, no. So for behavioral study, actually, this is a huge hurdle to overcome, more than you think. And then one time, and I was interested in losing, even still interested in losing weight. But anyway, one time I participated in a diet study. Yeah, so every week, and I had to show up to CRC and then have a nurse to measure my weight and take a blood. And of course, that's a diet study, but of course I start running. Because I wanted to impress the nurse, right? Because we became friends. So that's a monitoring effect. So this is regardless who get the drug and who don't get the drug. And people who participate to RCT, and then outcome from them could be much, much better than what you would see from observational study. Because observational study, people don't even know they're being monitored. And so they are free from this healthy worker effect or Hawthorne effect. All right? So this is a study I was hired as a statistician when I was a student. So this data is from a veterans study, the VA study. And what they did is that they did a randomized trial. And the randomized patient who are using, these patients have MI. So everybody had an MI and hospitalized. And half of them get aspirin only, and then other half get aspirin and Coumadin, warfarin, get combined therapy. Yeah. And then results are negative, completely Kaplan-Meier curves overlapped, right? And after enrolling 5,000 patients, an outcome for death, totally negative. And then what we did is we looked survival for the people who passed inclusion criteria, but they chose not to participate for reason other than clinical reasons. Okay, and then the VA, they have a national death database. So we checked their death, and then this is a difference we saw. So I could say this difference is much, much more than the effect of drug. It could be from healthy workers effect, people who participated, and then they may be the ones who wanted to do better anyway, and also the monitoring effect. And that put these people to survival much higher. Yeah. So the data from observational trial study and RCT are much, much different by nature, so we can never combine. Right. And then another problem with RCT is there's a problem with adherence. Okay, so this is a study published probably 2 years ago, 2013, I think, from a New England Journal of Medicine. So what they did is, what is the P? P is a patient who are undergoing dialysis. And then E, exposure of interest, is a drug called sinacosat. And that's a drug to help the side effect, not side effect, but you can see that. It should be improving survival among dialysis patients, because the people who are on dialysis, they have a high risk of dying. Okay, and then I think that the drug should be helping with people with kidney failure. Yeah, that's a drug. Can't explain more than that. But anyway, this is the result. In Kaplan-Meier, this is RCT, so they thought they don't have to do regression. So main analysis, and they chose to do unadjusted analysis by Kaplan-Meier curve. And p-value from log-log test for Kaplan-Meier curve was 0.11. So it was a negative result. Everybody was in shock. Anyway, and then so what happened? And this is graphing below. It's showing cumulative percent of protocol violation. So when you see placebo group in the first year, fourth month, 0, 4, these are months, study months. and more people start using calcinacalcet, and they're supposed not to use cinacalcet because they're randomized to placebo group, but they start using cinacalcet, and then some people who are randomized to cinacalcet stop using because of a side effect. Okay, so more and more contamination start to happen, and then we think that start masking effect. Okay, so effect of cinacalcet start to diminish with the more contamination between study drug and placebo. Okay, all right. So why did this happen? RCT, Principle of Statistics. Okay, and we call it intention to treat analysis. Analysis have to be based on people who are randomized, based on the drug who are randomized. Ignore the fact which drug they use. Okay, so statistician, we don't even worry about which drug they ended up to use. We just grab the randomized drug assignment and then draw Kaplan-Meier curve based on the randomized arm. Okay, so that's called the intention to treat principle, ITT method. Okay, and why do we do that? If we divide cinacalcet and placebo based on actual drug they use, we violate randomization, right? Because people who tend to move from placebo to cinacalcet may be the ones sicker, right? Yeah. So if we use that to form groups, then we don't have a beautifully balanced baseline, right? So what is the reason to randomize them? Okay, randomization is very costly, expensive, labor intensive. We still do randomization because we want to make sure two groups are the same, right? And that's why main analysis for RCT, we had to use ITT, okay, randomized arm, not actual treatment. So if the analysis followed user group based on randomization, but people start moving between arms, then the contamination happens, right? So RCT, even when you have a perfectly designed RCT, and it's hard to prevent this from happening, right? Yeah. And so that's the limitation of RCT. Yeah, it's the ethical problems, right? I can't say don't do it. Like if you are clinicians, you know patients are dying, okay? And you might just do open label, right? You go to shelves, lock the shelf, and look at the paper, find out which drug they are on. If they are on a placebo, you might want to switch it to a study drug. So we had one time, we were doing a multi-site studies, and Vanderbilt was coordinating center, and we got the phone call, and at one of the sites they want to go open label because of the patients and getting worse and worse. And then we have a huge debate if we should let them do it. I mean, they have a right to do it, right?
Isn't there a midpoint though? Like if you were to do a double-blind study, would there be a midpoint at which point you actually decide if you should unblind it or keep it that way? From a midpoint.
So when you have a double-blind, and so this is how, I don't know what the exact question you're asking.
I guess my question is, you said that the doctor will go in and take look at their charts and see what they're decide what, if you should just go ahead and give them a drug, which messes up the study, correct?
Right. I mean, what I recommend people to do is never even put the drug arm in your database. So even you're labeling A and B in your research database, if you label A and B, when you unblind one person, it unblind the whole people. Okay. So I'm telling people never even put a variable called the study arm. That shouldn't exist in your research database. Only the research pharmacy will have that. And all you have is ID, and then they have a list of ID and then A and B or actual treatment, and only they can see it. So that prevents unblinding one person will unblind the whole study, as long as you do it that way.
So presumably the people who they would want to unmask would be people who were doing poorly.
Right.
So if you counted all those people as, need to unblind as an event, then would that,
Right.
basically then
Yeah,
test
yeah.
the study at that point.
There are, yes, I get your point. You can do sensitivity analysis in many ways. So in this study, what they did is they censor patients 6 months after protocol violation happened. So that means after 6 months of the protocol violation, they take them out of this analysis. They're staying in the study, but just in analysis phase. And they pretend they never existed after 6 months. And that analysis actually showed a significant effect for the drug. So you can do many sensitivity analysis, but in the protocol you have to decide which analysis you use as a primary analysis. Okay, and so that usually go with ITT. So ITT means as long as people stay in the study, you use the data, and then arms, you go with the randomized arm. And if you want to use other approach, like the approach you have as a main analysis, you need to convince the committee. Okay. So as long as you have a strong reasons not to use RTT, they might let you to use alternative approach as a main approach. So they did like 10 different sensitivity analysis. They censor patients 6 months, 3 months, 1 year, or different time point, or they actually did regression adjustment, and then they did a very, very complex modeling approach, and all other evidence show drug worked. And only for this Kaplan-Meier curve, unadjusted ITT approach, and show negative result.
In this article, this question of doctors reassigning patients. So it seems to me like the only reason for a doctor to reassign a patient is the doctor has reason to believe that the patient who's on placebo, let's say, is going to benefit from the drug, right? But I mean, this is obviously an experiment, so you don't necessarily know that the drug is providing benefit. That's why you're doing the experiment.
That's right.
So does the clinician at that point, when they reach and uncover the label and figure out if it's placebo or a drug, actually have access to the statistical information to indicate that yes, there is a statistical benefit at this point in the study, and you should provide drug to that patient? Because otherwise it's kind of pointless, right? I mean, maybe
That's right.
they have this anecdotal feeling that the drug is going to provide benefit, and they feel bound to provide drug to the patient, but maybe statistically it's not even effective. So
Right.
How does that happen? And if it is statistically, if there is this big difference in terms of efficacy of drug versus placebo, then it seems they're ethically bound anyway to provide drug, right?
Right.
You can't just carry the study on for 10 more years and otherwise people pointlessly die
Right.
on placebo if it's already
So
benefit.
I know your point. So the problem is they did all these analyses at the end of the study. And so people who are needing to switch or switching anyway happen in the middle, right? So, of course, the physicians who participate in this study, and then they thought drug worked 50% and drug don't work 50%. They don't know the answer. That's why they did the experiment. So that's why they participate as an investigator. But in the middle of the study, they don't have evidence yet. But they are facing situations, people are dying. So what to do, right? So they thought they should do the best, do everything they could. So even though these are researchers, and then they thought they wouldn't do such a thing at the beginning of the study, but when they really faced it, and it happened. And then if you really worry about this, and you might put the monitoring plan. So you say you look at the data periodically during a study, and then if you know after 1 year, 2 years, in middle of the study, drug is working, and then you make a judgment whether everybody who are on placebo should be getting a drug or not. But in reality, we don't monitor that too often. Okay? So more look you do, you get penalized. So we will talk about when in the afternoon or tomorrow sessions. But anyway, so when this is happening, they don't know. They have no statistical evidence.
Well, I think that makes sense for the clinicians to not know. But I mean, shouldn't there be someone like yourself, a statistician, who's overseeing it? Let's say it's a 50-50
Mhm.
7 or 5 years, 10 years, whatever. But if you're studying an
Right.
MS that moves along, and clearly the curves are breaking apart,
Yeah, yeah.
it's definitely significant.
Yeah.
We have the same shit monitoring video analysis and decide that it's no longer ethical to withhold the treatment effect of it.
Right, so that's just my question. Does it
So
make
we-
sense
mhm.
to
Sometimes we-
those choices and
Yes.
so that-
So it's really the debate on whether how often we should look during a study, okay? And then there's a disadvantage in look too often. So the p-value, nature of p-value, we will talk about it when we talk about multiple comparisons. More p-values you compute, and then you start increasing chance of a false discovery, okay? So the p-value is 5% we judge, right? P-value is a chance probability of making mistake. And then if the p is less than 0.05, 5%, and you say it's okay. With a 5% chance, that's okay. And we ignore that chance and we claim drug works. But always 5% chance, and you're claiming it wrongly. You might say drug works even if the drug is not working. So if you look 20 times and each involve 5% of chance making mistake, okay? So if you look 20 times, and you might pick one time and for nothing, the drug seems working. And it just, you monitor too often, therefore you catch the trivial effect as a study result. So therefore we had to be carefully decide how many times we look, and the more look you do during the study, and then you actually penalize p-value. So you cannot use 5% to claim difference. So you make a bar much higher. So if you look after 1 year, and then you say in the protocol you don't claim p-value unless it's less than 0.001 or something, instead of 0.01. So that actually prevent you from making misjudgment by looking too many times. So it's really pros and cons. We're not really analyzing data as time goes on. So if you have 5-year study, we probably look, from my own experience, maybe twice. Okay. After 100, if you are designing 1,000 patient study, you might look after 10% are enrolled, and then the middle point after 500 people are enrolled. But we don't do 5 times based on my experience. Because of that reason, more look you do, and you get penalized yourself to the direction, so you can claim significance less than you would have. Okay. Right. So these are our problems with RCT, right? So typically, if you pretend you never listen to what I say last 30 minutes, okay, and many people never listen to my talk. So many people think RCTs have a strongest as evidence, and then observational studies are less. And then within observational study, prospective cohort study have a better evidence level than case control study, but the cross-sectional study is the least. Okay, so we have RCT, and then meta-analysis, and people do often. For some reason, we don't do it often as a biostatistician. But anyway, RCT comes first, and then prospective cohort study comes next. And then case control study, well-designed case control study maybe, and then retrospective cohort, it depends on the design, and then cross-sectional study at the bottom. So that's the evidence level. But anyway, what I wanted to say is, even though people think RCT is a gold standard design, and don't believe that, okay, you really have to look what happened in RCT, what happened in observational study, what is the analysis they did, okay? And then you make your own judgment. Right? So you don't think, New England Journal of Medicine, this is RCT, and JAMA, Lancet, I believe it. It doesn't work that way. You have to read the paper and read the method and make your own judgment. Okay, so that's the last, take-home message from this part of session. Okay. let me read it then, the summary. Right? Observational studies are easier to conduct than experimental studies, such as RCT. In such observational studies classified with three types, cross-sectional, cohort, and case control. You can't do risk for case control. Be careful with odds ratio and risk for interpretation. In observational study face a challenge in statistical analysis, and typically we use a multivariable analysis to control for confounding, and RCT may be okay with unit variable, which is unadjusted analysis, because they have a balanced groups. But anyway, don't rely too much on the likelihood of truth, and make your own judgment. Okay. And that's it. So we are done with the epi part of this course, and the rest of it is all statistics. So any questions? Oh, thank you. We're not ending here, but thank you so much. Good. So I think it's a little bit too early for bathroom break, so we will start on statistics. Okay. Or so what time is it now? We need a lunch break. What time? What time do you? 11. Okay. Oh, it's already. Ooh. Since I can't waste any minutes of your time, and I might just go with a little bit of a next sessions if you let me. I know you're hungry, but we'll see. Let me just check. So the org can do descriptive statistics. Okay. All right. So afternoon session. For 9 minutes, and I just give you introduction. We will be talking about stats, what is a p-value, and what is a hypothesis testing, and then we will talk about mean and standard deviation, median, interquartile range, and standard error and confidence interval. And then after that, we will be talking about how to select, when to use t-test, when to use chi-square test, and when to use correlation coefficient test, and so on. And we might not have enough time to do after that. But anyway, and then we have, I have a lecture on how to enter data. And probably these portions here, we talk about t-test, ANOVA, and chi-square test, and correlation coefficients, and we use a data set from Titanic. Okay. And so probably we won't be able to finish all of this in today. So many of hands-on probably goes to the tomorrow session. But anyway, so this is a plan for rest of today and probably half of tomorrow's session. All right, so let's take a lunch break, and then after lunch we are moving to the room next door.